Hello everyone. So, what we are discussing these days is plasma application, and we are very near to the end of our course. And in this phase, actually, we will be talking some of the very interesting application of thermal and cold plasma. And as I told you in the beginning that we will be excluding the fusion plasma area, but anyway, you know that this thermal plasma has ability to contribute in the area of the fusion as well. So that is a very important thing about the thermal plasma, and sometimes cold plasma also can contribute in the area of fusion plasma. So what I will discuss in this, the first one, what we already discussed in the previous class, the area of waste management. Now, in this, I will be talking a little bit about that, and gradually I will switch to the other application areas. So, the waste management sector, you have seen the amount of waste that is created by society every day, and they are not in kgs or hundred of kgs, they are in tons of tons they are generated, and you are addressing a technology which can address this kind of volume of waste for management. So, and not only that, what we promise that it is wealth from waste. Whatever waste you are generating, basically we will be converting that to some useful thing. It may be energy or it may be some other material which is of use. Now, the thing in the waste management sector, three quantities are very important in this field. They are the capacity, that is considering the huge volume of waste that is getting generated, how much of the waste you can treat per day. So this is the capacity. Efficacy, this is how much of the waste you can mitigate in a way that they will be non-existent over the earth. They will not occupy the physical space over the earth. They will be just become gaseous compound, and they will not be visible in open eye. Now the empowerment is that what empowers the plasma to qualify to address such kind of huge waste and the hazardous and carcinogenic waste, and doing that in a very environment friendly manner. So these things are basically the key features of any waste management system, and plasma is also in that. So now the first one I am coming, that the process rate, how many kgs you can mitigate per day. So that is usually written as TPD, that means that ton per day. Just to give you a feel that plasma, because of its intense energy and so high temperature, the process zone involves conduction, convection, and those reactions which are much faster compared to those reactions at lower temperature because of the presence of atomic species, ionic species, and other reactive agents. So just to give you a feel, these are say anion resins and cation resins. They are used in water filtration system in huge quantity, but as far as their mitigation is concerned, then possibly the plasma route is the only permitted route to mitigate that. You cannot dump it, and they don't usually get reduced if you keep it for many years. They just stay like that. So to mitigate, plasma is one of the wonderful ways that exists for this kind of anion and cation ion exchange reagents. You see that these are kept in boxes, and one box is usually say 5 kg, and doing that I have just run it. So the box is kept and the plasma is switched on, and now you can just watch your clock, and you will see that it is less than 30 seconds. Now it is done. So when we are talking, the 5 kg of this resin is processed, and you are seeing the plasma jet that is coming out. So you can see that how fast the process can be. So that enhances the process rate, which is very much demanding when you are addressing large volume of waste. So observe gasification. Just now what you have seen is 120 kg in 1 hour in this small reactor, and the rate can increase by say 3 to 4 fold if you are properly feeding the waste in a consistent manner. Now I come to the efficiency part, that this much volume of waste you have put in and how much residue that is keeping on the earth after the processing is done. So you are packing your MSW in these boxes and you are feeding into this plasma. This is actual photograph. I could have played this video. If time permits, I will show one such installation video in the tutorial class. And you see that when this is going on, the stack, this is the emission what is this is the stack through which the emission is released in the atmosphere. You can see that there is absolutely no smoke. And after the processing is done, this is the reactor bottom. It was a rectangular chamber, and what you are seeing, almost nothing is left at the bottom. And whatever was there, we collected, and it was only 26 gram. So what you are seeing, that 9 kg of waste box was packed to precisely determine what is the efficacy of the system, and that has been reduced to only 26 gram. So almost more than 99.7% of the waste is just converted into gas, and that is not occupying any volume on the earth. So that is the beauty of this plasma process, that conversion efficiency is extremely high. So during this time you will see that the emission, whatever the discharge that is released in the atmosphere, they are well within the prescribed norm. Now here you are seeing that what is allowing it to do the marble? It is the temperature that is the primary factor in this. And you know, the thermocouples, whatever we put inside the reactor, we need to save them because of the very high temperature. So usually we put it well within the wall so that it doesn't get damaged by the high heat flux. So there we need to do some interpolation to find the actual temperature, what may be inside. And you are seeing that it is 1473 Kelvin. It is also near the wall only. Okay. So just close to the wall, this is the kind of temperature that you are achieving there, and this is a direct, snap of the thermocouple reading, which was kept well within the reactor wall. So this is the temperature. As I told you, to break the bond, you need a temperature at least more than 1000 degrees centigrade, so that all carcinogenic components bonds are broken and they become the benign gas. Now, benign rather element, they may be gas or they may be something else, and in most of the cases they become gas because hydrogen combines to form H2, then N combines to form N2, and O combines to form O2. All of them are basically gases. Now you have seen that no smoke is there in this plasma incinerator when it is doing the operation. And here what you are seeing, this is a diesel incinerator which are commonly used, and you see that a kind of smoke they generate and they pollute the environment. So the fine particulate that comes out through this, basically this spreads all over the area, and we inhale them, and that causes many of the respiratory diseases. So these are no way allowed by our pollution control board. So and you see that the plasma incinerator is able to cause a discharge which is absolutely smoke free. Now when you come to the actual measurement, so we have measurement devices, and that measures continuously different discharges like NOx, CO2, CO, and you see this is another important thing, oxygen level. So you see that it is not disturbing the oxygen level which is there in the ambient as such, but when you go for this harmful emissions, you see that the red one is the CPCB limit. CPCB stands for Central Pollution Control Board, and this blue one is the emission that we have measured. using our instrument. You are seeing that the emission is always within the limit what is prescribed by the CPCB. Now, you know that we are talking about the waste management things using plasma, but you actually have not seen that. I thought that you should have a feel of inside of such reactors, and you can just have a look inside this. These are the refractory walls made of, high density alumina bricks, and this is the bed over which the waste forms. Just seeing the glow over here, that plasma incinerator, you can understand that whatever falls, they will be just immediately broken into their constituents, and they come out mostly in the form of gas. Now, coming to the this dioxin and furan, which are basically extremely carcinogenic in the level of nanogram, and they forms especially when you go for the incineration, open burning of the polyvinyl chloride kind of PVC kind of thing, and you see that when we are mitigating that inside your inside a plasma reactor, then this is the kind of vigorous reaction that starts happening over there. So just to give you a feel of the live plasma gasification process of such substances which are not allowed to burn in open air, because the open air you achieve a temperature which is usually less than say 600 degrees centigrade, and this is the ideal temperature to form the dioxin and furan from the polyvinyl chloride kind of substances. So when you burn in the plasma gasifier, this such vigorous reaction takes place, because so high temperature, the metal is coming and producing large amount of gas which is very hot and going up, and they are giving a suck at the bottom, and that is making the gas to rotate, because one side it is suction and another side the cold substances are falling, and that is making the gas to rotate in such vigorous manner while the gasification is taking place. So what you have actually, you have now have a feeling about how the plasma gasification goes as far as the normal open burning is concerned. So you can find the difference very easily, and you can really get a feel about the actual process that goes on inside the plasma reactor. And you know that CPCB approves only plasma gasification as the technique to mitigate this kind of plastic polyvinyl chloride kind of substances. Now, coming to the electronic waste management, this is an area which I told you that it is called urban mining, because you are getting very valuable materials out of these electronic gadgets which are not functioning and dumped in the waste box. So, what is allowing thermal plasma process to get to do the electronic waste management in such superior manner? So, these are the points that I have listed. Easy availability of high temperature. What we are doing here, actually it will be it will be 6000, 10 is missing here, it will be 6000 to 8000 degree Kelvin temperature. So this is easy availability in your plasma torches, that so 10 is missing here, just count that. So it is 6000 to 8000 degree Kelvin, that is easily available in plasma devices. Now, aggressive reaction via ionic and nascent atomic species, as I told you, they are possible only in plasma kind of systems. Then equal applicability to polar and non-polar materials. This is relevant because there are certain things like microwave incinerators, where microwave it works only on the polar molecules. When you are heating a dry substance in your microwave household microwave oven, you will see that the heating is not that efficient. But when you are using a wet substance, because of the polar H2 molecule, they get heated extremely fast. So, but in case of plasma, it doesn't. It is not a requirement that the substance to be polar or non-polar. It is equally applicable to all of them. Then it has extremely high enthalpy content, that is the joule per kg, which is basically increases the process rate. Then the process is very simple, rugged and compact. As I have told you in the initial slides that the plasma system, the torch is very compact, and the reactor you can make as per your requirement. So ultimate system becomes quite compact, and rugged. Now, extraction of energy from the organic content through gasification, they are all exothermic reactions. Whenever any carbonaceous material or hydrogen or some other substances, when they react with oxygen, they becomes oxide, and most of the cases the reactions are highly exothermic, and the amount of heat that is generated, as I told you in the previous class, that sometimes the total energy that is generated in the gasification process is 95% of that is coming from the waste itself, and only 5% what you are delivering outside through the torch. Of course, initially you are delivering only through the torch. Once the gasification starts and you start incinerating the gas that is being generated, then only this kind of figures come out, that 95% of the energy that is coming out from the waste itself you are extracting from the waste, and only 5% of the energy you are getting from the torch. That time actually you can just switch off the torch. You can run your system with the energy of the waste itself, and not only that, you can extract additional energy that has been generated in the process, and you can utilize that for other things like generating steam or rotating turbine kind of thing. Now, the process is much faster, and because the kind of gradient that you can maintain in a plasma because of so high temperature, that is so huge, so that conduction, diffusion kind of processes, that even the convection, because of the high temperature, you get a very very high speed of the jet. So everything makes the process of gasification much faster compared to ordinary burning what you get in open air. Now, in case of this electronic waste management, nearly 100% of the metal you can recover, and it has significantly high throughput. The metal that you get after the processing, I will show you some of the results. You will see that post processing is minimal, because almost pure material you get at the end. Now, here one is a process flow sheet that usually now consider for this electronic waste management using plasma. You see that we have packed the PCBs inside the boxes. So this is the box, then we drop into the plasma reactor, and you are seeing there that aluminum what was there, it is coming out from the slag port as a pure aluminum metal. Then whatever the iron components are there, the temperature is set in such a way that they are not melt, but they are loosened from the matrix on which it was installed. So now you can just put a magnet and take them all out without any putting much effort, and you can collect them like this. Then the loosened matrix on which the components were installed, now that just becomes like sand, and you can take out the copper which were interlayer in that matrix just like this. These are pure coppers, and connecting leads come out like this, and these leads sometimes contain the very precious metal. And here what you are seeing, just I have shown you in a bit expanded view. This is the the aluminum which is coming as pure aluminum. This is the PCB, this is the box in which you have packed, and this was taken, this photograph was taken when the actual processing was going on with the PCBs. Now you can see the beads kind of thing that you get over there. They basically contain the precious metals that has been there in the leads, and these are the ceramic, because there are lots of ceramic used in that PCB board, and these are the fiberglass. Usually these are used in the PCBs, recovered iron, and this copper. What I was telling, that mostly very pure form of the metals are getting extracted. As we have seen, the aluminum is very pure, and then the irons whatever you are extracting, because rest of the thing is gone, so this is almost pure iron. And whatever the organic things like this PVC covers and everything, they are volatile, they just get gasified, becomes gas, so they are not existent here. And the copper that you have extracted is more than 95% pure, because only slight paint kind of thing that is over there, otherwise it is completely pure copper. So compared to normal mining in this kind of urban mining, you are able to extract the constituents in a very pure form. Now, with this I conclude the your this waste management, including the municipal solid waste (MSW) and the electronic waste. Now I will enter into another very interesting application area of this thermal plasma. I told you that I will not be covering in this course the fusion plasma. I will be limiting myself to only thermal and cold plasma applications and their theories and diagnostics. But here, one thing that the thermal plasma can directly contribute to the fusion area. So this is a unique application of thermal plasma jets. Now, what you are seeing, mostly many of you have already guessed what this is. Actually, this is called tokamak, and this is the toroid within which the plasma is confined. Okay. Now, in this, actually, these walls which are there, they are supposed to contain within the core region the fusion plasma which are existing in millions of degree Kelvin. So naturally, if instability occurs or the other way, the diverter region here through which the extraction system, extraction of the plasma, whatever the debris or other materials which are to be extracted through this. So this zone is extremely stressed during the operation. So what should be the material for construction of the inner wall of the tokamak? So these are very much important to know. So new material development which can withstand extreme condition needs to be developed. Maybe there are pure metals, or maybe there are high entropy alloys, so which are nowadays is a very active field of research. So any of them, you need to develop material for this zone which may be exposed to very high neutron flux, very high flux of say ions and neutrals, and it can be subjected to tremendous flux of heat, which this may need to withstand. Not only that, the material, the particles which impinge on that, they can change their structural behavior, they can change their mechanical behavior. So all these things are very important to know to build such devices. But unfortunately, the kind of instabilities or kind of flux that you will be actually getting in the system is not easily available, mainly because these devices are still not operation, still not in operation. Some shots have been taken, but they are not sufficient to extend these facilities for development of materials, testing of the materials that is being now developed. So high heat and particle loads, both steady state and transient, that may be there in these tokamaks, that lead to erosion by the plasma, as well as high temperature thermal cycling, which can affect mechanical properties and lead to fatigue. Now, deuterium tritium uptake or retention, which adversely affect closure of the fuel cycle, tritium fuel cycle, and increases radiation safety risk. Degradation effects by helium, which are typically destructive to material when implanted in their plasma facing material surface by the plasma, or form deeper by neutron reaction. Now, neutron irradiation leading to material damages by atomic displacement and nuclear reactions within the plasma facing material. Now, this synergistic effect, whereby the high heat flux, high particle loads, out of equilibrium deuterium, tritium, and helium concentration, the effects of thermal transients and neutrons. So their synergistic effects combine in unexpected way sometimes to produce changes in the material properties and behavior that are outside the intended design limits. So we need to develop material and we need to understand what will happen to the material structure in such cases. So we need to have some experimental facility which will be providing us the desired ion flux, desired fluence, that desired Newton flux, heat loads, then long pulse duration in the fusion device, so that we can carry out our experiment and we can get sufficient time to do that. Now, control over the plasma material interface. So these things are not available in the fusion reactors because mainly they are still not fully operational, and also you know that this is a closed chamber. Putting the good diagnostic access is not that straightforward. So we need a system which can offer you all these, that desired ion flux, then fluence, then control over the plasma material interface, then sufficient time to do the experiment, not in just sorts of milliseconds, then good diagnostic access, desired heat flux, and if possible the 14 MeV newtons as well. Now the thermal plasma jets, what it can provide actually. Plasma material interaction facility using the thermal plasma jet can simulate the plasma facing material conditions in a test bed. It can give you fluxes 10 to the power 22 meter square per meter square per second. It can give good diagnostic access to the plasma material interaction region. It can give you steady state long time operation, so that you can finish your study taking sufficient time. Good control over the plasma properties by controlling the operating condition. Then it can offer plasma material interaction surface area few tens of centimeters square, and overall thing that it matters is the much reduced capital cost that is required, because this is a very simple system. You really don't need to build a tokamak reactor to get these experiments done. So you can do the material development without investing much money, making such simple system, and still you can know many aspects of this plasma material interaction under extreme conditions like those which occurs in the fusion plasma devices. So here I am showing one such device that has been developed inside in our lab, and you see that the plasma jet that has been generated by this device, you see that there is a pencil like beam. It is absolutely non-divergent, and the kind of heat flux it can provide, kind of ion flux it can provide, that is matches very well with the kind of condition that you may face during the in systems like tokamak. The first wall or the diverter region of these devices may face such extreme conditions. So what you need now, you need to put your material in front of this, and then you can expose the material for certain duration, and then you can check what changes has been happened to the structural properties or some other properties of the material through some diagnostic techniques. Now, so this is a thermal plasma jet which has been shaped by properly managing the electromagnetic body forces to generate a beam of this type, which is absolutely having no divergence and very thin pencil-like beam structure. So we call it HCLL, highly collimated long laminar plasma jet for material testing under extreme conditions. So with this, I stop. We'll meet in the next class for other application. This is plasma spray coating development, another very important area in the technological field. Thank you. We will meet in the next class.